In this video, we look at how complex numbers can be used to obtain some geometrical results. And this video has been prepared for use with the Unit 4 of the Further Maths specification for WJEC. In the previous video we saw how to find the nth roots of a complex number, and we now at this stage also need to realise that those nth roots will form the vertices of a regular n-gon when they are plotted on the Argand diagram. And we're going to have a look at how we can use complex roots to solve some geometric problems. We need a few key facts both from the Further Maths Unit 1 and also from Further Maths Unit 4. First of all, we need to remember how to work out the modulus of a complex number. And we need to note that the modulus of a complex number can also be calculated using the fact that the modulus of the complex number squared is the same thing as the complex number times by the conjugate of the complex number. So the modulus of z squared is the same thing as z times the conjugate of z. We know from Further Maths 1 that the modulus of z minus w represents the distance of the point representing z on the Argand diagram from the point representing w on the Argand diagram. Now, from our earlier observation, we can also say that the modulus of z minus w squared is the same thing as the modulus of z minus w times by the conjugate of z minus w, and the conjugate of z minus w is simply the same thing as the conjugate of z minus the conjugate of w. There's some results about transformations that we need to just recall. These again you may well have met in Further Maths 1. If we have the transformation z goes to cos theta plus I sine theta times z, or if you like z goes to e to the I theta times z, then that gives us a rotation around the origin of an angle of theta anticlockwise. And if we have a slightly more complicated transformation, z goes to a plus e to the I theta times by z minus a, then that gives us a rotation about the point which represents the complex number a by theta in an anticlockwise direction. And then in the previous video we looked at the nth roots of a complex number r e to the I theta, and we'll certainly be using that result again in the course of this video. If you think about plotting the nth roots of a complex number, they all lie on a circle of radius r to the 1 over n, so that's the nth root of r, and with centre the origin. And what's more, they are equally spaced, with each root being 2k pi over n away from the adjacent roots, which means that the nth roots of the complex number are going to form a regular n-gon with centre the origin and radius 1 over n. If z1, z2, z3 up to zn are the nth roots of the complex number re to the I theta, then they are certainly the roots of the equation z to the n minus re to the I theta equals 0. So we've got z1 plus z2 plus z3 plus all the way along to zn, that's the sum of the roots, must equal minus b over a, where b is the coefficient of z to the n minus 1, a is the coefficient of z to the n, so we've got b is 0 because there's no z to the n minus 1s in the polynomial equation, a is 1 because there's 1 z to the n, so we've got minus b upon a must be equal to 0. That result can also be obtained using geometric progression work. Okay, so our first example. We have to find the fourth roots of 16i in the form re to the I theta and illustrate the roots on an Argand diagram. We then have to think about the midpoint which joins two of those roots. But first of all, let's have a look at finding the fourth roots of 16i. Well, 16i has clearly got a modulus of 16 because it is 16 units away from the origin. And the argument of 16i is clearly 90 degrees or pi by 2. So we know that 16i is the same thing as 16e to the I pi by 2. So the fourth roots of 16i must be of the form 16 to the quarter times by e to the I pi by 2 plus 2k pi divided by 4, where k can take the values 0, 1, 2 or 3. Putting k equals 0, well, first of all we know that 16 to the quarter is just 2. With k equals 0, I've got 2e to the I pi by 8. If I have k equals 1, I've got 2e to the I times 5 pi by 8. With k equals 2, I've got 2 times e to the I 9 pi by 8. And finally with k equals 3, I've got 2e to the I 13 pi by 8. So, to draw these points on the Argand diagram, we first of all know that they all lie on a circle of radius 2 and centre the origin, because the modulus of each of the roots is 2. The first root has got an argument of pi by 8. That's about there. The second root has got an argument of 5 pi by 8. The third root has got an argument of 9 pi by 8. And the final root has got an argument of 13 pi by 8. So the four roots that we've got there form the vertices of a square. And we've got told that those 4 points are P, Q, R and S. Moving on to the second part of the question, we know that M is the midpoint of PQ. Suppose that point M represents a complex number Z. Then we are going to try and find the modulus and argument, first of all, of M, and then we'll try and find the modulus and argument of W, given the fact that M is a fourth root of W. So first let's consider M. What do we know about M? Well, looking at the triangle OPQ, we know that O to P is 2, we know that O to Q is 2, we know we've got a right angle at O. We also know that the angle from the real axis to OP is pi by 8, because the argument of the first root is pi by 8. So, Pythagoras, first of all, tells me that QP squared is 2 squared plus 2 squared, which is 8. So QP must be the square root of 8, or 2 root 2. M is the midpoint of QP, so that tells me that P to M is a half of Q to P, so P to M is root 2. If we think about the triangle OPM, it's right angled, because we've got the right angle at M, and we also know that angle OPM is 45 degrees. So we've got an isosceles right angled triangle, so OM is going to be the same as PM, which is root 2. That means that the modulus of Z is root 2. The argument of Z is pi by 8 plus angle POM, but angle POM is 45 degrees, or pi by 4. So we've got the argument of Z is pi by 8 plus pi by 4, so that is 3 pi by 8. So we know that M represents a complex number Z whose modulus is root 2 and whose argument is 3 pi by 8. So Z is the fourth root of W. That tells me that W is Z to the power 4. So the modulus of W is the modulus of Z to the power 4, which is simply mod Z to the power 4, which is 4. The argument of W is the argument of Z to the 4, which is 4 times the argument of Z, which is 3 pi by 2. So the modulus of W is 4, and the argument of W is 3 pi by 2. The fourth roots of W are going to be the vertices of a square with centre, the origin. M is one of these roots, so the other roots will simply be the other midpoints of our original square. Okay, let's move on to a second example then. First of all, I've got to write down all the sixth roots of unity. Remember, unity just means 1. We've then got to show that if the sixth roots of unity are Z1, Z2, Z3, Z4, Z5 and Z6, then the sum of those numbers is equal to 0. And then finally, we've got the points A1, A2, A3, A4, A5 and A6 form a regular hexagon inscribed in a circle of radius 1. P is a point such that the distance from P to the centre of the circle is 5, and we've got to produce a complex number solution method to find the value of A1P squared plus A2P squared plus A3P squared plus A4P squared plus A5P squared plus A6P squared. Right, for part A, well, we know the modulus of 1 is 1, we know the argument of 1 is 0, so we know that in the RE to the I theta form, we can say that 1 is the same thing as 1e to the I times 0. So the sixth roots of unity will be 1 to the sixth times by e to the I 0 plus 2k pi divided by 6 for k equals 0, 1, 2, 3, 4 and 5. In other words, we've got e to the nothing, e to the I pi by 3, e to the I 2 pi by 3, e to the I pi, e to the I pi 4 pi by 3, and e to the I 5 pi by 3. E to the naught is clearly the same thing as 1. So, moving on to part B, Z1 plus Z2 plus Z3 plus Z4 plus Z5 plus Z6 is 1 plus e to the I pi by 3 plus e to the I 2 pi by 3 plus e to the I pi by 3 plus e to the I 4 pi by 3 plus e to the I 5 pi by 3. We can view that as being a geometric progression with first term 1, with common ratio e to the I pi by 3, and with 6 terms. So the sum of that geometric progression will be r to the n, so that's r to the n minus 1 over r minus 1, so in this case that's e to the I pi by 3 to the power 6, take away 1, over e to the I pi by 3, take away 1. E to the I pi by 3 to the 6 is the same thing as e to the 2 pi I. So we've got e to the 2 pi I, take away 1, over e to the I pi by 3, take away 1. E to the 2 pi I is cos 2 pi plus I sine 2 pi, which is 1 plus 0i. So the top, e to the 2 pi I take away 1, is simply 1 take away 1. In other words, we've got the sum Z1 plus Z2 plus Z3 plus Z4 plus Z5 plus Z6 must equal 0. There is an alternative way of justifying that result, and the alternative way of saying it is that Z1, Z2, Z3, Z4, Z5 and Z6 are the roots of the polynomial equation Z to the 6 minus 1 equals 0. So Z1 plus Z2 plus Z3 plus Z4 plus Z5 plus Z6 is the sum of the roots, which must be minus b over a, where b is the coefficient of z to the 5 in the polynomial z to the 6 minus 1 equals 0, and a is the coefficient of z to the 6 in the polynomial. Well, the coefficient of z to the 5 is 0, and the coefficient of z to the 6 is 1. So our value of minus b over a is minus 0 over 1, which is 0. So we've shown that Z1 plus Z2 plus Z3 plus Z4 plus Z5 plus Z6 must be equal to 0. So let's now move on to part C of the question. It's certainly well worth your while having a diagram here. Now what we're going to do is we're going to set things up in such a way that we're going to set the axes up in such a way that the origin is the centre of the hexagon, and the point A1 is going to represent the complex number 1 plus 0i. The remaining vertices of the hexagon will represent the other 6th roots of unity, because we know the 6th roots of unity form a regular hexagon with radius 1. So A1 represents 1 plus 0I. We'll have A2 representing the second root of unity, which is e to the I pi by 3. A3 representing the third root, which is e to the I 2 pi by 3, and so on. We know that P lies on a circle of radius 5 units and centre the origin, so the modulus of W must be equal to 5. Now let's start by having a think of what we can do with A1 P squared. So A1 P squared is the distance between A1 and P squared. P is represented by W, A1 is represented by Z1, so A1P squared is the same thing as the modulus of W minus Z1 squared. Now we know that the modulus of W minus Z1 squared is the same thing as W minus Z1 times the conjugate of W minus Z1, and the conjugate of W minus Z1 is simply the conjugate of W minus the conjugate of Z1. So if we multiply that out, we have W times W bar plus Z1 times Z1 bar minus Z1 W bar minus W Z1 bar. Now we know the modulus of W is 5 because the distance from P to the centre of the circle is 5, and we know that P is being represented by the complex number W. So W bar is the modulus of W squared, which is 5 squared, which is 25. We also know that Z1 bar is the modulus of Z1 squared, and we know that the modulus of Z1 is 1. So Z1 bar is going to be 1. So A1P squared is 25 plus 1 minus Z1W bar minus WZ1 bar, which gives me 26 minus Z1 W bar minus W Z1 bar. Now we can do exactly the same thing for the other 5 points. And if we add the results, then we end up with A1P squared plus A2P squared plus A3P squared plus A4P squared plus A5P squared plus A6P squared is 6 lots of 26 minus W bar times by Z1 plus Z2 plus Z3 plus Z4 plus Z5 plus Z6 minus W times by Z1 bar plus Z2 bar plus Z3 bar plus Z4 bar plus Z5 bar plus Z6 bar. Now we already know that Z1 plus Z2 plus Z3 plus Z4 plus Z5 plus Z6 equals 0. And taking the complex conjugate of that, we can deduce that Z1 bar plus Z2 bar plus Z3 bar plus Z4 bar plus Z5 bar plus Z6 bar is simply the complex conjugate of Z1 plus Z2 plus Z3 plus Z4 plus Z5 plus Z6, which is the complex conjugate of 0, which is itself 0. So our expression for a1p squared plus a2p squared plus a3p squared plus a4p squared plus a5p squared plus a6p squared simplifies drastically to 156 minus the complex conjugate of w times by 0 minus w times by 0, which gives me 156.